Hi, hello, good morning, all. Myself, Rahul from Chipetch Technologies. Happy to see you all this wonderful Saturday morning. All came to this session to enhance your knowledge in VLSI. So, we have an exciting interactive element planned for you, a pool that will be popping up in the chat window shortly. So, I encourage all the attendees to participate in this pool. So, you will have the pool right now. So, just start filling the details and we can take it from there. So, meanwhile, let me introduce you our speaker. So, without further ado, her name is Miss Mittu George. She's a DFT engineer at Celton Semiconductors Private Limited with the MTech in VLSI design and embedded systems. So, Miss Mittu brings a wealth in knowledge and experience to the table. Currently, she plays a pivotal role in Celton Semiconductors, ensuring a seamless integration of DFT principles into chip design. So, throughout today's session, we'll be seeing what is DFT, the importance of DFT engineers in designing a chip, how to build the skills required to become a DFT engineer, and career growth opportunities in the industry. So, before I pass on the podium to Ms. Mitu, I encourage every one of you to participate in the pool. So all your questions will be answered after the session. So in case if you have any questions during the session, you can just post it in the chat window. So once the session is over, Ms. Mittu will answer all your questions. So in case if you have any concerns in taking this pools, like you can just let me know. You can just put your query in the chat box. So now the pool has been started. Yeah, like people who have participated, I encourage them to take the pool now. So without now further delay, I will just pass on the baton to Mittu and just enlighten the journey. So Mittu, over to you.
Thank you, Rahul. Okay. So a very good morning to all who has joined for this technical talk. So let's start our webinar without much delay. So today we are going to discuss about what is the role of a DFT engineer in SOC design and its career opportunities. So let's start with an ASIC flow. So I am planning to explain with a basic ASIC flow. Later, you will come to know where the DFT engineer will come into picture. So every ASIC flow, as you know, it starts with specification. So what is meant by specification? As you all know, the customer requirements, whatever it is required, it will be documented properly and it will be kept as a reference for the other cross-functional teams. So whatever be the customer requirements, it has to be captured properly at this stage, because this is going to be used as a reference in the further stages. So this documentation will be used by other cross-functional teams in their coming stages. So the next step will be the RTL description stage. So here the RTL engineers will try to write an HDL code based upon the specification which they have got. So it can be in any of the RTL code, like in any of the HDL language, like Verilog or VHDL. Once it is done, the next stage is it will be given to synthesis. So what is meant by synthesis? So the input to the synthesis stage will be nothing but your HDL code. This HDL code will be converted into a gate level schematic at the end of this synthesis stage. So here, synthesis means actually it is consists of basic three steps. Like it will translate, optimize, as well as it will map your design into the gate level equivalent. So what is happening here? The logic which you have captured based upon the customer requirement during the RTL description stage, now it will be translated in terms of Boolean expressions now. Once this is translated in terms of Boolean expression, the next step is that it need to be optimized. It will be optimized in such a way that it will be giving an optimized expressions. Once it is done, the next stage is it will be mapped into the corresponding gate level netlist. So the output of the synthesis is nothing but a gate level netlist. Once it is done, the next stage it will be given to the physical design people. So as you all know, there it will happen, the floor planning, placement, routing, clock tree synthesis, everything will be performed at this stage in order to get an optimized design in such a way that it will consume a very less area. At the same time, the performance will also need to be met at this stage. Once it is done, the next it is given out for tape out. Tape out is nothing but it will be given for fabrication. So the output of the next, like the output of fab is nothing but our semiconductor device itself. So whatever customer requirement which we have captured at the initial stage, now we can see it in the form of a manufactured device which is on the silicon or a semiconductor wafer here. Once it is came out, now the next is that in between we will perform various testing process and all. After testing in wafer level as well as in die level, it will be given for packaging. So after packaging also we will perform the package level testing. Once it is done, it will be, if it is error free and if it is defect free, it will be now shipped to the customer. So this is the basic ASIC flow. Now here where DFT engineer will fit into. So before explaining that, let us understand what is DFT, what is design for testability. So design for testability means it's basically a technique of adding testability features into an IC design. Now, or we can also define it as a method of we are developing some test vectors and we will apply those test vectors onto the design. Now, why it is required? Why we need to develop the test vectors and we need to apply it onto the device? Or why we need to add some testability features into the design? So that we want to know now, right? So we are giving once this is designed, we will be giving the design for the fabrication, right? So during the time of manufacturing, anything can happen to the design. Anything can happen in the sense manufacturing defect can happen to the design. So if it has occurred, who will test at that stage? Or how we will come to know whether the manufacturing defect has occurred to the device or not? So that need to be analyzed properly, right? So in order to check whether manufacturing defect has occurred to the design or not, we need to add some testability features to the design prior to its manufacturing. Then only once the device is got manufactured, we can test it properly and to check whether the manufacturing defect has occurred or not. If it has occurred, we can separate those defective components. So the purpose of DFT, or what DFT means, we are actually adding some testability features into the design so that once the device got manufactured, if it is returned from the fabrication or from the fab, we can test the device in order to detect any manufacturing defects are there in the design or not. So it has to be included or it has to be added into the design prior to the manufacturing itself. Then only we can test it once it got manufactured. So what we will do here is we will develop the test vectors as well as we will develop all those things prior to the manufacturing itself. So once it is manufactured, we can use these test vectors and we will be applying this onto the manufactured device and we will compare whether the expected response is getting matched with the observed one. So like that we will compare. So DFT is nothing but we are adding some testability features to the design and thereby we are we are making the design testable. Now, what is the importance of DFT in chip lifecycle? So we will see one by one. So DFT actually ranks as one of the top concern for SOC design. Why? Because we know that the design is keep on growing day by day. Now the design is going keep on growing day by day in the sense the logic inside the SOC design is keep on growing. The logic can be anything, like it can be digital or analog or the memory designs within the particular SOC. So it's keep on growing. At the same time, the IO pins which is available to access or to test the design is very restricted also. So here comes the importance of DFT. With the limited IO pins itself, we want to check the entire design or the entire logic within the SOC. Now, DFT is considered as an integral part of high-level design process. We cannot fit DFT after a particular stage itself. DFT actually comes into picture from the day one itself, from starting from the specification until up to the packaging. DFT will comes into picture. Not only after up to the packaging, after the packaging also the DFT will be there. So we cannot strictly speak that DFT will comes after the synthesis or before synthesis. We cannot strictly fit DFT into a particular stage. It will be there from the starting stage itself. So because of this reason, DFT is considered as a an integral part in SOC design. Now, reduction in feature size is also another important point. As I told, we know that we are like semiconductor industry is keep on changing from technology nodes from technology node day by day, right? So when we are going into the small feature size itself, what is happening there? Into the small the chip area, we are trying to incorporate more and more devices, right? So the logic is becoming more and more dense now in the same area which is available. So at the same time, as I told before, the pins which is available is also restricted, but still we need to test the device, right? We need to make sure that it is working fine and there is no defect within the device. So now, what is the role of a DFT engineer now? So as I told that, the role of DFT engineer is to ensure that all the defect in the manufacturing chips are identified properly. So after manufacturing, actually defects can be there within the device, right? So it's the responsibility of a DFT engineer to ensure that all the manufacturing defects that has occurred is detected properly. We need to detect it properly, otherwise it will otherwise what will happen, we are actually trying to ship the defective parts to the customer, which will result in a huge loss to the company itself. So it's the responsibility of the DFT engineer itself to detect all the defects that has happened into the device at the time of its manufacturing. Now let's go through some of the DFT terminologies. It all sounds similar, but it's different from each other. So let's see what is meant by defect. So defect means nothing but the imperfection or a flow that happened into the design during the manufacturing. So as we all know, IC manufacturing means it's very prone to defect. Even a small speck of dust can also cause a defect within the IC. It can result like as a metal short, if an extra metal, if it is deposited during the manufacturing, if it is an unwanted metal deposit, it can act like a metal short. If there is any deficiency, like if suppose a material is not getting deposited properly, then it can also act like an open, right? So these all things can cause actually a defect. So defect is nothing but we can just define it as something some flow that is happening when we are manufacturing the device. So as I told, a speck of dust can also result in defect to the device. Now, what is fault? Fault and defect both are different. So, fault here is nothing but the representation of your manufacturing defect. As I told, there are in DFT we have different faults here. We are modeling the defects into different types. Bridging faults are there, stucket faults are there, then transition faults are there. It's based upon the defects that is happening into the design. So for a small example, I can explain about like stucket. What is stucket? As I told, sometimes an extra metal deposit is happening. So the pin itself will act as it is stuck at to value 0, or if it is stuck at to value 1. So that can be characterized, or it can be modeled as a stuck at fault. So fault is nothing but we are representing, it's a way of representation of a manufacturing defect that has happened. Now, what is meant by failure in DFT? So we have some, like, we can define it in such a way that the device is actually causing a large deviation from what it need to perform. For an example, as I told that, one second. As I told, suppose an extra metal deposit is happening. As I told, this is our AND gate, right? Suppose this is the AND gate. So this pin is actually, let it be connected to VDD. So if it is connected to VDD by its functionality, means what? This value will be always acting as it is connected to logic high. Now, I don't want this pin also to be get connected with a logic high, but because of some extra metal deposit, actually some shorting has happened here. So now what will happen is this pin, the second pin, will also act like it is getting connected with the logic high value. So now if I'm trying to give here value 0, I am expecting my output to become as 0, because we know how an AND gate works, right? When any one of the input of an AND gate, if it is 0, the output will change to 0. But because of this extra material deposition, what is happening here? This is also forcing the other pin to be at value 1. So now what will happen? Even if you are giving the value 0 here, this will act as it is stuck at value 1. So now what we will be getting as the output? The output will be always permanently at 1. So we can say that this pin is acting as permanently as stuck at 1. So this pin, that is, I'm going to name it as pin B and this as pin A. The pin B now acts like permanently it is stuck at 1. Because of this fault, you will be always getting the output as 1, even though you are changing the second input to 0. So what is happening here? You are finding a huge deviation in the performance of the AND gate itself, right? So failure is nothing but you are not getting the intended function of the design. That is mainly because of that defect that has occurred during the manufacturing. So you can see that there is a large deviation in the performance of that particular device that has occurred because of this manufacturing defect. So here in DFT terminologies, defect has its own meaning, fault has its own meaning, then failure has its own meaning. So, or even though these three terms look similar, it is different when it comes to the DFT. So now, how to test the device? So how, as I told at the starting, we DFT is a process of developing some test vectors and we are applying those test vectors, right? So what is meant by this test vectors? I will explain this with the help of a simple AND gate. So consider consider this AND gate and let us take how the tool will generate the patterns for testing this AND gate. So here you can see that this is a 2-input AND gate, right? So how you will tell that this AND gate can perform the 100% as we are expecting? If you want to tell that, or if you want to give a guarantee that this AND gate will work as it is intended, you can ensure or you can guarantee this only if you can if you can test the pins A, B as well as C. That is, you have to ensure that there is no defect that has occurred to the pin A then to the pin B as well as to the pin C of the AND gate. If there is no defect occurred to these 3 pins, then only you can say that this AND gate will work as you want. So you need to, as a DFT engineer, we need to test and we need to come into a conclusion that there is no manufacturing defect. So how the tool will take care of this? So let us say that here you can see you can see consider the pin A. So there are 2 possibilities for this pin A. The pin A, it can be either stuck at 0 or it can also stuck at 1. We cannot predict which fault will appear to that particular pin, right? It can be either stuck at 0 or it can be either stuck at 1 during the time of manufacturing. At the same time here, for the pin B also that possibility is there. It can be either stuck at 0 or it can be stuck at 1, right? Then what about the output pin? That is C. This pin C can also be stuck at 0 or it can be stuck at 1. So if you are counting now, what are the different possible defects, stuck at defects that is happened to this pin? You can count here. So 1, 2, 3, 4, 5, and 6. There are 6 stuck-at fault possibilities that can occur to this AND gate, 2-input AND gate. So we need to test all these 6 stuck-at whether it is existing there or not. Then only we can, if none of the 6 stuck-at faults is happening there, we can tell that this is like there is no manufacturing defect has occurred in terms of stuck-at fault modeling. Similarly, we have other fault models also. So I am just speaking only with respect to the stuck-at fault because this each fault model is actually it's beyond the scope of this discussion. So how to find out? So we can take an example of how to find out whether the pin A is stuck at 0. Let's take an example. So, 1 second, let me take the pen. So, consider the pin A. I want to find whether this pin is stuck at 0. So, how the tool will take care of this? If you want to find out whether the pin is stuck at 0, the first method is that we need to activate or we need to apply the opposite value to the pin A. So if it is, if you want to check whether the pin is stuck at 0, we need to activate the pin A with the opposite value. So we are going to check it as stuck at 0, right? So we need to give the opposite value, that is logic 1 at the pin A. Same way, if you want to check stuck at 1 whether it is there at the pin A, at that time you need to give the opposite value. If you are checking for stuck at 1, you need to give 0 value at the pin A. So here we are going to check for whether stuck at 0 is there or not. So you need to give the value 1, which is opposite to the fault which we are considering. So we need to give here 1. Now, from the truth table of AND gate, you all know that in order to get whatever we are giving at this pin A at C, we need to give here the value at the other pin as 1. Then only whatever we are giving here at this pin will be propagated to the output C. If you are giving here the B as 0, whatever input which we are giving here, it will not be reflected at the output. We will be always getting output as 0. So what we need to do is at pin B we need to give 1 if it is an AND gate. Then only the value which we are giving at the A pin will be propagated to the output here, right? So here, if I am getting the output at C as 1, what is the conclusion now? We can conclude that there is no stuck at 0 happened at pin A, right? Because I'm giving here 1 and I gave 1 here in order to check whether stuck at 0 has happened at the pin A or not. If you are getting output as stuck has 1, we can conclude that there is no stuck at 0 has happened at the pin A. The same way, the same pin we can also can be checked whether stuck at 1 second for stuck at 1 has occurred or not. If you want to check for stuck at 0, you need to give the value as a 0 here. Now, how you will conclude? This time, you need to get the value as 0 at the output. If you are getting 0, that is, if you are able to propagate this value here, and if you are able to get the value 0 at the output, this means that the A pin is not stuck at 0. There is no stuck at 0 fault here. So you can see the possible test vectors to check stuck at 0 and stuck at 1 at the pin A. Uh, so these are the test vectors. Same way, the same approach you can use to find whether stuck at 0 and 1 is happened at the pin B or not. Not only at the input, you need to check at the output pin also, whether stuck at 0 or 1, is it there at the output pin also. So you need to check for the all the pins of the AND gate. And if you are able to prove that there is no stuck at 0 or 1, you can say that this there is no stuck at fault is there in the design, and AND gate can work as it is required. So here you can see that totally 1, 2, 3, 4, 5, 6, 7, 8 vectors are there. But the tool will not apply all those 8 vectors, because if you are observing these vectors, you can see that some of the vectors are redundant here. So the tool will apply vectors in such a way that it will cancel out all the redundant vectors, and it will choose only the appropriate vector. So you can see here 1 1 is here, right? So the remaining 1 1 from the other, it will not see all those things. And you can see here 0 1 is there, and this 0 1 will not be considered. Then 1 0 will be considered, and this 1 0 will not be considered, because it will automatically cover the other stucket also. Now, what about 0 0? So 0 0, this pattern is actually checking for stuck at 1, right? Stuck at 1, whether it is there at the output. Stuck at 1, whether it is there at the output, is decided based on whether we are able to get 0 at the output or not, right? So this can be achieved. This pattern can be achieved either by 0, 1 or 1, 0. So we are already covering this pattern or this pattern with the help of these patterns. So we need to consider only the 3 patterns here from the all these 8 patterns. So in order to check this 6 stucket fault of a stucket faults of 2 input AND gate, we now need to apply all the 8 vectors. We need to give only 3 vectors. So tool will apply only the 3 vectors in order to test whether any of the stucket fault is there at any of these pits. So this is how the tool will generate the patterns. Now, as per DFT, when you will tell your design is completely testable. So this is very important. In DFT, a design is said to be completely testable if all its internal nodes are able to be testable. Testable in the sense we must be able to control as well as observe all the internal nodes. You can take the previous example itself. This is an AND gate, right? I'm taking the AND gate as an example. So when you will tell your AND gate is completely testable, if you are able to control the value at each of its pin, which means control in the sense if I want to test this pin A as well as B, I must be able to give either 0 or 1 at the A pin, and I must be able to give 0 or 1 at B pin also. Similarly, at C also, I must have the freedom to control the value either to 0 or 1. Then only I can check whether stuck at 1 or 0 is there at each of the pins, right? So the controllability should be there at each and every node of the circuit. The same way, I should have the observability also. As I told, in order to check the stuck at 0 at this particular pin A, I am applying some 1 with the help of the controllability which I have. Not only controllability, I need the observability also. Whatever I am applying here, whether it is taking as it is, I need to observe it at the output. If I have that observability, then only I can tell whether that stucket is there or not, right? So as far as a DFT is concerned, in order to tell the design is completely testable, I need the complete controllability and observability at each and every node of the design. So this is the case of an AND gate, right? Similarly, for the entire design, this controllability and observability is required. Then only it is possible to confirm from our side, right? There is no defect has occurred like that. So DFT is actually a collection of methodologies to create a design testable. So as I told, we are adding some testability features into the design. Now, for what? We need to control and observe the each and every pin or every internal node within the design. So you can see the same AND gate here. We have input A and B and output C. So all these nodes, if it is able to controllable as well as observable, then only I can tell that this AND gate is completely testable. Now, what is the goal of a DFT? So the main goal of DFT is to ensure the quality as well as at the same time we need to reduce the test cost and we need to increase the volume production also. We should not delay in the overall production. So increase the quality in the sense by DFT, we are actually not trying to improve the functionality of the design. We have no role in improving the functionality of the design. We are only checking whether the manufacturing defect is detected properly or not. Suppose from the specification, if RTL team has captured wrong specification, based on that only the synthesis will happen and the remaining steps will be happening, right? So we are checking whether the design is manufactured properly or not. But we are not trying to improve the functionality of the design here. The quality in the sense we are trying to improve the quality by means of our testing means that we will ensure that none of the defective part is getting shipped to the customer. That has to be assured from the DFT side. Now, test cost reduction. So what we are going to do is we need to test the entire device, but at the same time we need to reduce the overall test cost also. How it is possible? Possible in the sense we have different faults, right? We need to cover all the faults within the design in such a way that we need to use only a minimum test vectors. As I told you, can take the example of the AND gate. We have 8 vectors are there. We are not going to apply all the 8 vectors, right? We have the minimum 3 vectors. Using that, we are going to test the AND gate. Similarly, for the entire design, we need to reduce the number of vectors which is required. Thereby, we can reduce the test cost also. How it is related to the test cost, you will come to know in the coming slides, because we need to test this with the help of a tester machine, which itself is very costly. So consider an SOC. So what is an SOC? SOC can be considered as a complete system on a single chip, right? If we can group the complete logic in within the SOC, we can group the logic within the SOC into 4 groups mainly. It can be digital logic, it can be analog or memory or IOs. So DFT will classify the entire logic within the SOC into these 4 categories: digital, analog, memory, and IOs. Why this classification is that for in DFT, we have different approaches for testing each of this logic category. Digital logic will be tested in a different approach. For memories, we have a different approach. For testing the IOs and testing analog logic, we have different testing structures actually. So based on that, we will test the entire SOC by considering it as different 4 groups of logic. Now, what is basically meant by testing? So testing is nothing but we are sorting the DUTs in order to determine its acceptability. So here you can see that, as I told, we will be generating some patterns prior to the manufacturing. So this will be generated before the manufacturing itself. And what we will do, once the chip comes, we will be applying these patterns onto the chip with the help of a tester machine. So what we will do is that we will observe the response here. So the manufactured chip will be giving some response. So we will consider it as an observed response, and we will compare this response which we got from the tester machine with the expected response which we have already stored in the tester machine. If both are matching, then we will tell that the testing has occurred correctly and there is no defect in the device, and the testing is said to be a pass. Now, if you are observing some deviation from the observed as well as the expected, now the possibility is that the device will be defective. Now we have to throw it to the dustbin. There is no other go because the device is already manufactured. But now we have to also perform another step here, which is known as diagnosis. So at a diagnosis stage, what we are going to do is we need to point out what is the root cause for this failure, why the response is not matching each other. So that response we need to actually figure it out, and this can be recorded for the coming project or for the future enhancement. So that diagnosis need to be done once we are detecting there is a mismatch in the response. Now, you can see, as I told, we have a tester machine in order to test the device once it got manufactured. So, as any other devices, many manufacturers are available with a different type of tester machine. So you can see here the important parts of a tester machines. We will be having a probe card with some probe needles. Here you can see some probe needles are the probe needles. So probe needles will supply the electrical inputs to the wafers. We will be applying the response with the help of this probe needles. So probe card is nothing but that is responsible for providing an electrical contact between our DUT as well as our tester machine. Now, how what is happening inside the tester machine? We will see briefly. So, as I told, there will be a semiconductor wafer. A tester machine will be applying the patterns to the wafer. Now, we will be applying this with the help of that probe needles. Now we will be comparing the response, right? So when we are getting a mismatch with the response, we have to locate those dyes on the wafer, and here by the process of inking we will mark those dyes which is showing a misbehavior, like which is not matching with the expected behavior. Now how you will mark those dyes on the wafer? This is done with the help of a wafer mapping mechanism, which will locate the particular defective dye with the help of an XY coordinate information. So we will mark those dyes which is showing some mismatch in the behavior from the expected and they observe. We will mark it with the help of an inking mechanism. Now the next step is sorting. We need to sort out this defective dyes. We don't want to ship that to the customers. So we will dice all this dye from this wafer, and the next part is we need to sort it out. From the good chips we need to keep it aside, and the bad chips we need to bin it. Only the good chips, like the good dyes, will be sent for packaging. Once the packaging is done, again these steps will be carried out in order to check any defect has occurred after the packaging also. So this is how the testing will take place. So you can see that how the inking is happening. So you can see here the wafer. On wafer surface, we will be marking the bad dyes. It's like a pen. We will mark out those defective dyes based on the results which we are getting. Now we need to sort it out which all are the good dye and which all are the bad dyes. So this will happen based upon some criteria. Like we have some expectations, right? This voltage need to be met, this much clock speed, electrical power, this should be the heat output, all those things. Those dies which are not meeting these things will be removed by the process of sorting and binning. So the next important terminology here is that yield. So how many good chips are produced during the manufacturing is nothing but our yield. So we have, suppose we have manufactured some 1,000 chips. Out of 1,000, suppose only 500 chips are good chips without any defects means our yield is nothing but just 50% only. Now, the next term is that there is another important term known as DPPM. Yield is measured in terms of DPPM also. DPPM means defective parts per million. Out of million devices which we have manufactured, how many is defective? So this DPPM can be measured only from the customer returns. That once we have shipped the product, sometimes some defect can be there, so the customer will return or they will point out these defects are there with the products. So from the customer returns only the DPPM can be measured. So yield is nothing but the number of acceptable chips out of the total manufactured chips. So the yield loss can also happen. Like after the manufacturing, this can be because of the random defects during the manufacturing or because of the process variation. On a wafer, we know that during the manufacturing at the different part of the chip, there will be some process variation. So because of that also yield loss may happen. Now, the another term is there, which is known as reject rate. So in DFT, reject rate means what? Sometimes faulty chips also will appears like a good chips. So the number of faulty chips that is passing our final test out of the total number of chips that is passing the final test will give us the reject rate. So you can see here some status of IC here. So here sorry, so here you can see these are the good chips. Good chips, those who are passing the final test will be considered as it is working. Now, good chips are there, but because of the testing, it appears as a failed chips. The chip is actually working properly, but because of the shortage, short means some problems within the testing, it is appearing as a failure chip. So this is actually will result in a yield loss. Now coming to here, bad chips are there. Bad chips are passing our final test. Here you can see this is basically a bad chip. It is has some defects, but because of some problem with the test cases or with the problem with the tool, it may be it will appears as a good chip. Now it is passing the test and it will go for packaging and it will be shipped to the customer. Those chips are considered as what? Test escape. So the bad chips which is failing the test, it's causing no problem. It's considered as a not working chips only. The problem is with this test escapes as well as with the yield loss. Good chips that is coming as a failure one will cause a yield overall yield loss, as well as bad chips that passing the final test will result in a test escape. So we need to consider or we need to be more conscious with this test case and yield loss. So nowadays, as you know, the density of the logic is getting increased. So before it was DPPM, now the industry is using DPPB, like defective parts per billion instead of defective parts per million. So now, with respect to manufacturing test, so the overall chip cost you can see here, it is a combination of the development cost, manufacturing cost, as well as the test cost. Our aim is to reduce the test cost, which is getting contributed to the overall chip cost. So how we can reduce this test cost? As I told, our tester machines are very expensive, and if the number of test vectors we need to apply to the device, if it is increasing, the memory which is required to store those test vectors on the tester machine is also will become more. So this will demands a high expensive tester. So the more time which you are spending on the tester machine, the more will be the testing cost. So our aim is in such a way that we need to reduce the time which we are spending on the tester machine in such a way that we need to come up with less number of test vectors. At the same time, we need to cover all the manufacturing defects that has occurred within the device. Thereby, we can reduce the test cost, which is getting contributed to the overall chip cost. Now, manufacturing a test, as I told, this is used in order to, what we are doing here is we are detecting, we are testing whether any manufacturing defect has occurred or not. Once it is done, we will perform the process of diagnosis. So what is diagnosis? So we need to pinpoint what is the main cause for this incorrect behavior of our device. What caused the device to give a such behavior, that need to be diagnosed properly, then that need to be documented properly so that it can be used for the coming projects, as well as for the same project for the next respin we can contribute to it. Now, as I told, starting we have seen just a normal ASIC flow. Now you will come to know where DFT will play a role. As I told, DFT cannot be kept strictly into a particular stage. From starting from the specification to the end, DFT engineers plays a big role. So what is the role of DFT engineer at the specification stage? As I told, when the customer requirements are captured, we need to fix the DPPM target also. What should be the maximum allowable DPPM target that need to be fixed at this stage? Now, with respect to DFT, we need to plan something like what should be the tester machine which we require for the testing, and how many test pins are there, and what must be the size of the memory which it is required to store the test pattern, how much time will be required for testing the particular device. All those plannings with respect to DFT need to be done at the specification stage itself. Now, the next stage, as I told, it will be RTL code, right? So RTL coding stage, what is the role of DFT engineer here? So as I told, SOC will be grouped, or the logic inside the SOC will be classified into 4 groups: digital, based on digital logic, analog logic, IOs. So as I told, there are different testing mechanisms for each of this group. So we have to confirm here which all testing mechanism we need to employ. So boundary scan, nothing but the JTAG. If you want to test the IO boundary, IO pins, JTAG need to be implemented. If there is memories in the design, MBIST need to be added. Now, if we want to go with the XP testing, it's another fault modeling. If you want to test for the transition fault model, we need OCCs and all. So all those things will be planned prior prior itself, and if it is decided properly with respect to this JTAG, MBIST, OCC, the equivalent RTL code will be added at the RTL code stage itself. Means with respect to DFT, whatever logic need to be added will be integrated at this RTL coding stage itself. Now comes the synthesis stage. So during synthesis, what is happening here is already we have added the DFT related blocks, everything here. Now all the flops will be converted in terms of scan flops here, scan stitching, and in an SOC level, different subblocks will be there. So all this DFT integration at the block level will happens during the time of synthesis. Once synthesis is done, it will be given for the physical design. So at this stage, scan chain reordering, if many MBIST are there, means MBIST controllers will be there. We need to group the MBIST controllers. Then timing check, then pattern generation need to be done here at this stage. Till here, it will be considered as a pre-silicon stage. After the physical design, we will be giving the database for the fabrication. From here, the post-silicon stage will happen. After the fab, the output is nothing but a silicon wafer, right? So now the design is got manufactured, and now it is coming in front of us in the form of a semiconductor device. Once the silicon brings up, we need to test the entire design, right? So again, we need to go with the digital testing, memory, analog, IOs, everything need to be tested once the silicon bring up has happened. So this testing will take place at the die level, as well as at the means at wafer level, as well as at die level. Now, if those dies which are working will be given for the packaging now. So now the product has came up. Now product level also we need to ensure that there is no defect has occurred. So there is no defect at the product level, then it can be shipped to the customers. Now, suppose any defect has occurred after the packaging. So as I told, diagnosis need to be done. What is the root cause for this failure need to be pointed out here. So this can be documented for the further respin, or it can be incorporated in the next coming projects. So root cause need to be diagnosed. So this is how DFT and the DFT engineer will come into picture in the entire SOC design flow. So this is how. So DFT is nothing but we are adding the testability features, and we are not going to do anything with respect to the functionality. We are just checking any manufacturing defect has occurred or not. Then we have to make sure that none of the defective parts is getting shipped to the customers. So I hope it is clear what is a DFT and what is the scope of DFT in chip design. So now for the career opportunities and all, I'm calling, I'm handing over to Rahul.
Thank you, Mittu, for this wonderful session. I hope everyone participated in this session got an insight about DFT. So we will be having this kind of webinar sessions on every third Saturday of every month. So the next webinar session will be on 20th April. And also we have few free courses in DFT. I will share the link. I will share the link with you shortly through the chat board. You can use that link to inquire, and you can register. So our learning advisors will be in touch with you and help you in taking these courses. So now coming to Chipedge, like I want to give you a few insights about who we are. So as I earlier said, I am from Chipedge, and Chipedge is founded in the year 2012, and it's managed by professionals. So we are into this industry for close to 11 plus years, and we have trained close to 4,500 plus engineers, and we have 200 plus hiring companies, and we do give 100% placement support for all the programs. So coming to the programs, we have programs in internship and multi-semester model. So internship programs are 4-week, 8-week, and 16-week. And the specializations offered are RTL design, design verification, design for test, physical design, and analog layout design. So the models and duration would be from 3rd to 8th semester, and the models would be 2 to 4 weeks of internship after every 4th and 6th semester, and would be 12 to 16 week of internship programs the 8th semester. So in this multi-semester model, for every semester, you would be doing this program for like 40 hours to 60 hours. So, and also we do industry relevant projects. So these are the courses what we offer. We offer courses for freshers and working professionals, for corporates, as well as for educational institutions. So for freshers, we offer specialized courses for the entire digital and analog VLSI design circle. And these classes are offered weekend as well as weekdays. So placement assistance and mentorship is given. So for corporates, we offer customized courses for both new hires and laterals. And these classes are also offered during weekend and weekdays. So for educational institutions, we have train the trainer program for improving faculty skill levels, certification programs for students delivered in colleges. So self-paced programs, we have design for test, design verification, RTL design, and physical design. So these are the courses what we are offering in self-paced. So you can learn these courses anywhere, anytime, according to your wish. So the courses offered are RTL design, design verification, design for test, physical design, synthesis, and sign-off STA. So the upcoming courses are formal verification, TCL scripting, and Python scripting. So these are the courses what we offer for the freshers. It's physical design, design verification, and design for test. So all these courses are 6 month and 4 month courses. This is a full-time course. So there would be 600 hours of interactive learning, assessment after every module, and we also have placement assistance. The best part is we also have no cost EMA option for these courses. So this is how you choose a course. So in case if you're good at digital electronics and CMOS, you can become a physical design engineer. So if you're good at analog electronics and analog layout, you can become analog layout engineer. And if you're good at digital electronics, analog electronics, and CMOS devices, you can become DFT engineer. And if you're good at programming and digital electronics, you can become a design verification engineer. So that is it from my end, guys. So now the all the questionnaire session will be answered by Ms. Mittu. So in case if somebody has any other questions regarding this, you can post it here. And also in the form which I have shared in the chat board, you can register to this chat board. So the advisors will help you in how to register for the free courses. What I told you, it is a self-learning course. It would be an added advantage in your resume. All right, guys.
Okay, thank you, Rahul. So here in, I can see a few questions here. So Srishti has asked, what is litho violation? So during fabrication, I hope you know about the basic fabrication steps and all. So we will have that photo masking and all, right? So if properly, if it is not masked, extra what metal deposition, all those connections can happen, right? So that is what known as litho violations and all. During the time of manufacturing, it can happen. Now, Chandra Mohan has asked, what is SOC, right? SOC means a system on a chip. So it's like a complete system on a chip. Like it will be a combination of what your it will be having memories, like various other sub blocks will be there. Complete system. We are actually keeping it on a single chip. Okay. Then Rohit, he has asked, he is a fresher and trying to get a DFT job. What will industry expect from a trained fresher like that? If you are a fresher, like you can get, actually, if you are a fresher, like a recently passed out, you can try attempting to get into the industry if you are getting trained from any of the VLSI means a training institute. It will be an added advantage because there they will train you in such a way that whatever industry requires, based on that the training will be given. So that will be an added advantage. Like a company is looking for those who are having industry related skills. So it will be less work for them also to train you if you know something regarding that. So what I prefer is like get trained from so the training institute and get a knowledge in DFT. If you are interested in DFT, get trained in DFT, then try to attend the interviews and all. So industry, I hope this is clear. Amar, bad chips in what sense? So with respect to the FT, as I told that from specification, RTL engineers would have captured everything correctly. We can assume like that, and we can proceed like the remaining steps, right? So everything is perfect till the physical design or till the tape out. Once the tape out is done, during manufacturing, anything can happen. As I told, it's not in our hands, right? Like some kind of test or any small minute mistake which is happening at the time of this manufacturing, it can cause other problems also. As I told, it may happens like a shorting, or it can acts like an open circuit. So this will what it will create is like the entire behavior of the chip itself will get deviated. So that can be considered as a bad chip itself. You can take the example like an AND gate. You are designing an AND gate. Because of manufacturing defect, some shorting has happened. Now you are actually packaged it also, and you are shipping it to the customer. As far as an end customer, I want, if I am applying 1 I want my output to be 1. If it is 0, what will be the customer reaction then? So will be those chips need to be considered as bad chips itself. If there is any defect that has occurred during the manufacturing, we cannot ship it to the customer, right? It need to be properly sorted out, and the defect free chips only can be shipped to them. So that's what I meant by bad chips. So, if a person having basic knowledge of digital analog, what should be prefer, STA or DFT? So, in any of the VLSI stream like RTL or verification, PD or DFT, digital knowledge is actually an ad, not it's required actually, because you know that electronic devices is nothing but basically it is the basic, it's nothing but digital circuit only. So if you are a fresher, if you are going for any interviews and all, the first stage of the first round will be with the digital questions only. So if you are how much you are thorough with the DFT or PD or whatever it is, the first stage need to be cleared, right? So digital is very much important. That basic knowledge should be there. You must be I tell you must be a master in digital also, not only for DFT, for any of the VLSI course if you are trying for. Then what does tape out? So tape out means once the fabrication, as I told, till the physical design, you can, if the entire ASIC flow is there, right? So entire ASIC flow, if you divide into two, you can divide it as a pre-silicon stage and a post-silicon stage. So pre-silicon means till that stage, you don't manufacture anything, right? You are designing it. There is nothing in terms of circuit there in your hand, right? So after physical design, the database is given to the fab for fabrication. Once the fabrication is done, the return whatever you are getting from the fab is nothing but your semiconductor device. Now you can see your device got manufactured and it is in the form of a wafer or in the form of a die. So tape out means like you are giving the database for manufacturing. So, what are the latest automation tools or technique used in DFT? So here, DFT, like the main stages is that you have a scan insertion stage. After that, you have a pattern generation stage. Once the pattern generation, then you have simulation. Then after that, we'll be giving for tape out, right? Everything once it come back to us, then the next it is diagnosis. So you can consider it as a first stage and all. So at each stage you have a specialized automation tools are there. So in synopsis, if you are going with for scan insertion, you have DC compiler and all. Then if it goes to the pattern generation, means if you want to generate the vectors, right? For that we are using Tetramax and all. So simulation VCS tool is there. Like that, for each stage, each vendor is providing their own tool. Mentor graphics, cadence, synopsis, all are coming up with the specialized tools. How can we predict the manufacturing test? I didn't get your question. How can we predict the manufacturing test? I didn't get that question. What is AC or DC scan capture shift? Capture and shift. Can you elaborate that? I'm not able to get. Are you talking about the scan insertion procedure, I guess? So if it is in fault model and all, if it is stuck it and all, So you will be using slow clock, right? You need to shift in the pattern. After that, you need to come into the function, like you need to capture it, the response. Then you need to shift it out to see whether any fault is there or not. Are you asking about that? Oh, not clear. So DFT engineer only checks manufacturing defects and not design functionality. Yeah, that's true. As a DFT engineer, we are not bothered about the functionality of the design. Whatever it is captured functionally, we want to make sure that none of the manufacturing defect has occurred to the design. If it is there or not, that only we will check it out. Functionally, whether it is giving correct or not, functional wise, we are not at all bothered. How we would test the chips to know whether they are defected or not. So as I told, we will generate the patterns before manufacturing itself, and once it is manufactured with the help of tester machines, we will be applying the same vectors, and we need to compare the response. So we are expecting a similar match. If it is not there, something would have happened during the manufacturing. Or the second case is we need to recheck the vectors, test vectors which we have generated. If we are sure that that's not the problem with the vectors which we have generated, then the problem would be with the manufacturing. So how to do the fault diagnosis? So diagnosis itself is a huge concept here. So uh, it cannot be covered now during this session. Now, which field, DFT or PD engineer, which job have a best job as fresher level student? So both is having its own opportunities. Both DFT and PD is having job opportunities. As a fresher, as I told, it will be an added advantage if you are getting trained and you are trying for a job. So instead of directly applying, try with a training institute, get it trained properly, get grasp the knowledge, and try in industry. After will every company industry will have different kind of training will be different based upon the tools which they are using. So what you have to do is get the basic knowledge in what is the, like if you are interested in DFT, get the knowledge of the means get thorough with the concept, and after that get into the industry. So remaining with respect to the tool, the company will be giving the basic training. Also, so currently now they are saying for 2 plus 3 plus years experience only. So as a fresher, even fresher openings are also there. So many service-based companies, you can see that they are posting for fresher level also. So that's what I told. If most of them are asking for trained engineers at the fresher level also. For DV course, no need for analog and the CMOS. For DV, you need to be thorough with your digital concepts. Then coding, it's important. If you are more interested in coding and all, you can go for DV. Then CMOS and all. See again, it depends upon when you are going for attending an interview and all, what kind of questions you will get. It depends again. So basic knowledge, if it is there in CMOS and analog, it will be also an added thing, added advantage actually. You cannot completely neglect, but CMOS and all, it's important. But main weightage will be given for digital basics of coding. You can expect all those things. Can you tell please about the more placement? For placement assistance, uh, you can contact Chip Edge directly. Okay. I have learned digital VLS to analog. What foundation knowledge? Uh, Basically, for analog VLSI and all, compared to digital, the job opportunities are very less. So, like in order to get into the analog job opportunities, it's very difficult unless you are from the IITs or NITs. So better to stick on to digital VLSI itself. For PD or any other course, do you provide access to Cadence or Synopsys tools? This you can contact, like, I think Chipetch, they are offering for Synopsys tools. How long it will take the access to be provided? It depends upon which type of course you are choosing. You can contact them. They will give a clear picture. Job opportunities for available for freshers. As a fresher, if you are trained, as I told, it is very easy to get into industry. It depends again into your interest, whether you are interested in coding or if you are interested in coding, you can be an RTL design engineer or you can be a verification engineer. So it depends upon your interest. Based on interest, get trained and start attending the interviews. We can class by working motion. And what is at-speed testing and all? Okay, so at-speed testing in transition, as I told you, different fault modelings are there, like stacked fault model, transition fault modelings are also there. So whether if you are applying a value 0 or 1, for an example, your pin, and you can take the example of an AND gate itself. The pin is at 1 itself. For one pin, you are going to change the input from 1 to 0. So how much time the pin is taking to get the transition from 1 to 0? All those things will be covered with the help of at-speed testing. So it's a vast topic actually. But recent PD domain is industry place. DFT domain, which companies with chip placement. With respect to placement and all, you can contact directly with the chip edge. They will provide you the proper guidance. I hope I have answered all the queries. Now I'm calling, I will hand it over to Rahul.
Thank you so much, Mittu, for this wonderful presentation. So, for all the participants, thank you so much for this interactive sessions. Like, you can always post your questions in the questionnaire session. So, coming to our upcoming weekend courses, we have design verification course, we have design for test course, we have RTL design course. So, design verification course is upcoming on 6th April. The design for test course is upcoming on 21st April. The RTL design course is yet to come out on 4th May. And design for test, again, we have another design for test course, which is starting on July 6th. So, except design for test on 21st April, except that course, all the other courses will be Saturday and Sunday. So, Saturday would be the theory session and Sunday would be the lab. And this design for test course, Sunday only, will be having theory as well as lab only on the Sunday. So coming to our offline courses, we have design verification and physical design test, and this is a 6-month course, which will be offline. Like you have to come to our center for doing this course. So the first batch of design verification and physical design will be starting on 10th June, and the second batch of design verification and physical design will be starting on 8th July. All right, now you can, in case if you have any questions, you can now post it in the chat board. And also we will now give the link for registration in the chat board. Whoever is interested for joining this course, or if you have any other concerns, or if you have any other questions, or if you want to join a short-term course or any other courses, you can also register there. All right, guys. Thank you. Thank you so much.